This video is the second part of chapter 6.2. We are going to focus our attention on the molecular geometry and also polarity of the molecule. After you finish watching this lecture video, please start working on part 2 of the online homework. In this video, we are going to focus mainly on molecular polarity, which is the polarity of the whole molecule. The molecular polarity can be determined by the molecular geometry that we learned from the previous part, the previous video, and also the overall dipole moment. So this is what we are going to take a look at, the overall dipole moment. So in order to determine the dipole moment for each bond within the molecule, you are going to need to recall from the previous chapter section. Okay, so the dipole moment from the previous chapter section is in chapter 5.1, page 74. Okay, so if you recall this, you will see that we can determine the bond polarity from the difference in the electronegativity between the two atoms that are sharing electron with each other. So if you recall, or if you go back to this page 74 on your lecture manual, you will see that if the electronegativity difference between the two atoms is between 0 to 0.4, we consider these to be non-polar covalent bond, right? Because they are sharing electron equally between the two atoms. There's no separate partial charge, right? So one will not be able to pull electron harder or stronger than the other. They are sharing equally. And another one that we look at is when the difference in electronegativity is between 0.5 to 2, right? So we consider this to be polar covalent bond. Okay, anything beyond 2, that would classify as ionic bond. Okay, so as I mentioned earlier, so how do we determine molecular polarity? Well, we are going to need to determine the overall dipole moment, right? And the overall dipole moment is need to be determined from the bond dipole, right? The dipole moment within the bond, and also the summation of that dipole moment, right? Whether they are going to cancel out or they are going to share electron equally, right? So for example, the simplest example would be the binary molecule. Okay, binary means 2 atoms, right? So you will see 2 atoms here. Okay, so if you see the molecule that contains 2 atoms, it's very easy because all you need to do is find out the polarity of the bond, right? So for example, in this case, if you look up the list of electronegativity value, you see that the difference between hydrogen and hydrogen would be 0, right? So this is going to indicate that the bond between these two are sharing equally. So this bond right here is non-polar. Okay, so this one, if you subtract, it's come out to be 1.9, right? Actually 0.9, right? So it would be 0.9. Okay, so let me write this. The difference in electronegativity here would be 0. This one would be 0.9. Okay, so this one would be 1.9, right? Okay, so according to this number, if you go back to what we talked about earlier, right? So if you go back to this previous slide, 0 to 0.4 would be non-polar, 0.5 to 2, right, would be polar. So according to that list, you will see that this is going to be non-polar. This one would be polar. This is also going to be polar. Okay, and how do I determine the positive or negative partial charge here? So this is delta symbol. It means partial. It's not full charge. Okay, so the reason why I need to use this symbol because it's not completely positive. This is not completely negative. They're still sharing electron, but this is going to be able to withdraw electron density away from hydrogen a little bit more, right? So the electron density is actually going to go toward chlorine more, but they are not ionic compound. Okay, so they are only partial charge between those two. So chlorine has partial negative charge because chlorine has higher ability to withdraw electron according to the value of the En. Okay, therefore, the dipole moment will go toward chlorine because this is telling you about that chlorine, the direction of the electron that will be pulling is going to be pulling toward chlorine. That's what it tells you. Okay, same thing for hydrogen and fluorine as well, right? So this one is polar bond, and the direction of the dipole moment is going to go toward fluorine, because fluorine has higher ability to withdraw electron toward itself according to the En value. After we know the bond polarity, the next thing we need to take a look at is the polarity of the molecule. Since these three molecules contain only one bond, right, between those two atoms, so that means the bond polarity of this going to determine the molecular polarity. So since the bond polarity in hydrogen is nonpolar, the molecule would also be nonpolar molecule. And because hydrogen chlorine are sharing electron unequally, and is making its bond to be polar bonds, therefore the molecule of these would be polar molecule. Same thing for hydrogen fluoride as well, like HF, right? So because this is a polar molecule, it's have polar bond, therefore the molecule would be polar molecule. Okay, so the polarity of the individual bonds or the bond dipole and the molecular geometry dictate the overall dipole moment. Okay, so this is linear, so that's why we are able to determine that very easily. Okay, so the next thing is, what about if we have more than one single bond, right? So we have, like, for example, this molecule right here, right, it's contain one group of bond, another group of bond. So how do we determine that, right? So same thing here. What you are going to do is you are going to determine the bond dipole first. The bond dipole between carbon and oxygen is going to be polar. Carbon and oxygen here is also polar. However, because the molecule is not sharing only between two atoms, right? This contains three atoms. Therefore, you will need to look at the overall dipole moment. You're going to look at the summation of that, right? So if you're looking at these, the direction of the dipole moment is going toward oxygen, because oxygen has higher ability to withdraw electron from carbon. Same thing for this as well, right? So it's going to go toward both sides of the oxygen, right? Therefore, in this case, it's similar to like tug of war. Okay, so because they are pulling in both directions equally, so therefore the summation of the dipole moment on both sides would come out to be zero, because they are going to be able to cancel each other out. Therefore, this molecule, would be non-polar molecule, because the overall, right, these two dipole moment will cancel each other out because they are pulling electron on both sides equally. Therefore, the molecule would be non-polar. Okay. However, if you have a molecule, like let's say like water, for example, the molecular geometry of water is not linear. Electron domain geometry of water is tetrahedral. And because we introduced two lone pair, therefore the molecular geometry is bent, right? So that means the molecular geometry of water would be bent. So the bent molecular geometry will help us determine the direction of the dipole moment overall as well. So for example, in this case, if you're looking at the direction of dipole moment here, it's going to go toward oxygen on both sides. And because on these both sides, right, they are nothing to cancel them. They are not able to cancel each other out because it's not in a linear geometry, is in a bent geometry. Therefore, in this case, the overall dipole moment will not equal to zero. It's going to go up toward oxygen, right? Because both of them are go up toward oxygen. Therefore, because the overall dipole moment is not equal to zero, this molecule is considered to be polar molecule. Okay, so let me summarize this thing real quick. Okay, so pretty much what you are going to determine is that first, you will need to determine the molecular geometry of the molecule. Okay, have to be the correct one. If you draw the incorrect molecular geometry, then you will not be able to find out the correct dipole moment. Okay, if you know the correct molecular geometry, then you are going to look at the bond dipole moment. Okay, and also the overall direction of the dipole moment. If the overall dipole moment are able to cancel each other out, come out to equal to zero, then that molecule would be nonpolar. If the overall dipole moment come out not equal to zero, which means they are not able to cancel each other out, then that molecule would be polar molecules. Here are the electron density for the carbon dioxide molecule and for water molecule. As you see, the red region indicate the high electron density and the blue region indicate low electron density. And as you already see, right, the oxygen has a higher ability to withdraw electron. Therefore, the electron density would be a lot higher in the oxygen regions. Okay, so therefore in this case, because both oxygen are pulling electron equally on both sides, therefore the overall dipole moment equal to zero. So that's going to indicate that this molecule would be nonpolar. Okay. However, for water molecule, as mentioned before, right, the molecular geometry of this is bent. So the electron density is going to go toward oxygen because oxygen has higher En, right? So as you can see here, the oxygen would have higher electron density. Therefore, there is nothing to cancel that, right? So the overall dipole moment going to go toward that oxygen, right? So therefore, in this case, this molecule would be polar because oxygen would be, this part right here would be partial negative, and this part right here would be partial positive. Okay. So molecular polarity is similar to tug of war. So pretty much if you know bond polarity, you know the molecular geometry, then you should be able to find out molecular polarity by looking at whether they will be able to cancel each other out or not. For example, if the molecular geometry is linear, like this, so this, if this were central atom and those are the outer atom that are pulling electron on both sides equally, then the molecule would be nonpolar. If you have trigonal-planar geometry and all directions are pulling electron equally, then the molecule will be the nonpolar molecule as well. If you have tetrahedral and all directions are pulling electron equally, then that molecule would be nonpolar. However, if you have the molecular geometry such as bent, this molecular geometry will not allow the two type of bond polarity will be able to cancel each other out. Therefore, the overall dipole moment is going to go in one direction. So that means the overall dipole moment will not equal to 0. It's make the whole molecule to be polar molecule. Okay, so the red indicate the overall dipole moment. Similar to trigonal pyramidal as well. If you're looking at trigonal pyramidal, they are pulling on this side, right? So pulling downward. Therefore, the overall dipole moment will not be able to cancel each other out. So it's going to go downward. So in this case, the overall dipole moment would be not equal to 0. So this molecule would be polar. Since we already know how to determine molecular polarity, we are going to revisit page 107. Okay, so we are going to take a look at the example on the xenon dibromide. Okay, so we're going to take a look at the bond polarity in the molecule and also the overall dipole moment. Eventually, we are going to predict the molecular polarity of this molecule. To predict the molecular polarity of the molecule, first, you will need to use the correct geometry of this molecule. We already determined molecular geometry of this, which is linear, right? So we're going to look at this linear geometry between bromine, xenon, and bromine. The second thing is you are going to need to look at the difference in electronegativity value between the central atom and the outer atom, right? So between bromine and xenon, there is no value of the En value report for xenon because xenon is in group 8. Okay, so therefore in this case, clearly bromine would have a ability to withdraw electron from xenon. So the overall dipole moment, right? So if you're looking at this is going to be polar bond. Okay, so it's going to pull toward bromine on both sides, but because linear geometry, therefore this tug of war right here, since they are pulling both sides equally, the overall dipole moment for this molecule would be 0, right? Because they are able to cancel each other out. Therefore, this molecule would consider to be non-polar molecule. Okay, so that would be the conclusion of this example. So next, we are going to also revisit page 108 as well. Okay, so we already looked at how to determine their molecular geometry. So if you're not familiar with this, again, rewatch the previous video, chapter 6.2 part 1. Okay, so which is a post before this video. So pretty much if we want to determine molecular geometry, molecular polarity, again, you need to find out molecular geometry first, okay? And then we are going to determine the bond polarity, and eventually we're going to look at the overall dipole moment. Okay, so I'm going to focus on these two because these two, the chemical formula are identical. However, the arrangement in the 3 dimension are different. So that's why the name of these two are slightly different, right? This is trans, this is cis, indicate the location, the different location of the fluorine. Okay, so we know that the molecular geometry of these two are octahedral. So I'm going to go ahead use that geometry. Okay, so this is octahedral, and if you look up the En values, you are going to see that these are the En value for all of those. Okay, if you look at the difference, right, between sulfur chlorine and sulfur fluorine, you will see that all of these contain there are polar bonds. Okay, so that means I'm going to use the arrow to indicate the dipole moment. The dipole moment between sulfur and this fluorine is going to go toward fluorine because fluorine has higher En value, right? Same thing for this chlorine as well. It's going to go to those. Okay, so now if you're looking at this geometry here, the next thing after you know the bond polarity, then you are going to look at how they are will they be able to cancel each other out or not, right? So what I would like you to do is do one thing at a time, right? So looking at things that is opposite. For example, in this case, this sulfur right here has two fluorine, right, that are on the opposite side. Therefore, the strength that are pulling on the top and on the bottom would be equal. Therefore, in this case, you will be able to cancel each other out. Okay. Now, if you're looking at sulfur and chlorine here, the chlorine would pull electron toward itself. So the chlorine will pull electron toward itself, and another chlorine also pull electron toward itself as well. So therefore, in this case, the two direction here is going to be able to cancel each other out. Same thing for these two opposite direction as well, right? They are going to be able to cancel each other out because they are pulling equally on both sides. Therefore, this molecule would have the overall dipole moment equal to 0. So this molecule would consider to be non-polar molecule. Okay. However, if you're looking at the cis structure right here where the two fluorine are close together, you are going to see that same thing, right? We are going to need to determine the bond polarity first and look up the dipole moment, right? So in this case, dipole moment going to go toward fluorine, go toward chlorine. The reason why I use this one is thicker than this, because if you're looking at it, the En value between, the difference in En value between sulfur and fluorine is much higher than sulfur and chlorine, right? So that means in this case, fluorine would be able to pull electron toward itself stronger than sulfur and chlorine here. Okay, so if you're looking at this, right, if I'm looking at the opposite side, clearly these two will not be able to cancel each other out. As I mentioned, fluorine has a stronger effect to pulling electron to itself than chlorine. So therefore, the overall dipole moment will not be able to, will not equal to 0. Okay, same thing for these two direction is going to go pretty much toward fluorine because fluorine has a stronger strength to pull electron than chlorine. Therefore, the summation of this part right here is going to go toward fluorine. However, between these two chlorine are the same, so that means this part right here will be able to cancel each other out. So therefore, because the overall dipole moment is not equal to 0, it's actually go up toward fluorine, right, toward these two fluorine here. Therefore, this geometry or this molecule right here that is cis conformation is going to be polar molecule. So that means, as you see, even though sometimes the chemical formula are the same, but if the arrangement within the three dimension are not the same, it can cause or it can result in different polarity of the molecule. Okay, so how you determine that? Okay, so again, it's going to be determined from first molecular geometry, second is bond polarity, third is the overall dipole moment, right? And eventually you can derive to the conclusion of polarity of the molecule. Okay, so in this case, our conclusion of these two molecules is that the cis structure versus the trans structure versus cis structure, they are going to be different in this part right here. So on the exam, you don't need to memorize what is trans and what is cis. All you need to do is that you need to, if I give you these two structure, you need to be able to tell me which one is going to be polar, which one is going to be non-polar from the analysis that I teach you earlier. Okay, so the next thing we're going to take a look at is going to be silicon tetrachloride and also dihydrogen sulfide. Okay, so what are the molecular polarity of this, right? So let's take a look at silicon first. So these come out to be non-polar because the overall dipole moment, if you're looking at this, right, is surrounding by the same atom. So they are going to eventually pull electron equally on all directions. So therefore, this molecule would be non-polar. However, the dihydrogen sulfide contain two hydrogen that connected to sulfur, right? The molecular geometry of this is bent. So that means because it's bent, they are not on the opposite side. So therefore, in this case, you will see that they are not going to be symmetrical. They are not going to be able to cancel each other out. So this molecule would consider to be polar molecule. Okay. So now my question is, go back to water again. If I draw a picture of water like this, would you think that water would be polar or non-polar according to this? Some might say that, well, because the dipole moment will go toward oxygen, right? And this is look like a linear, so they are going to be able to cancel each other out, so the net dipole moment should equal to 0. So that means the overall molecule should be non-polar, right? The answer is no. Okay, so again, this is a misconception that students always make a mistake on the exam. Okay, so the structure that I'm giving you here has nothing to do with the molecular geometry. This is just the Lewis structure. You will need to use Lewis structure to determine molecular geometry. The correct molecular geometry of water is not linear because electron domain, right? There are 4 of them. 4 electron domain is tetrahedral, but because you introduce 2 lone pairs, so that means water would actually be bent. The correct one would be bent geometry. Okay, so this is just Lewis structure. When you draw Lewis structure, you can draw any structure you want, right, in any geometry, as long as you have the correct connection and the correct number of atoms. That is going to be correct Lewis structure. So that means Lewis structure doesn't tell you the geometry or the shape of the molecule. When you are going to determine the shape of molecule, you will need to count the number of electron domains and also the number of lone pairs, right? So this is the correct geometry, which is bent. Okay, you need to use the correct geometry in order to find out the polarity of the molecule. Okay, so in this case, as I mentioned earlier, because oxygen has higher En value, so it's going to pull electron toward itself, the overall dipole moment will go toward oxygen. Therefore, this molecule would be polar. Next, we are going to take a look at the large molecules such as fat or oil molecule. And we're going to take a look at how can we predict polarity of this big molecule like this, right? It contains a lot of carbon and hydrogen. So pretty much when you're looking at fat molecule, it's going to contain 2 parts. One is going to be part of the hydrocarbon. Hydro mean hydrogen, carbon is mean carbon, right? So this part contains most of it with carbon and hydrogen. And also fat or oil also contain this bridge as well. You are going to learn this in Chem 123. Okay, so this part right here contains carbon and oxygen. Okay, so pretty much I'm going to circle them into region. Okay, so one is the carbon and oxygen bonds. Okay, so bond between carbon and oxygen is going to be polar bonds. How do you determine this? Again, you need to go look up the difference in electronegativity value, right? You are going to see that this bond right here would be polar bond. Same thing if you're looking at this bond between carbon and hydrogen and carbon-carbon, you are going to see that the difference in electronegativity value will fall into the non-polar bonds. Okay, this whole part are non-polar bond. This small section right here is polar bonds. So if you think about this, you have majority of the molecule to be non-polar. Tiny bit of the molecule, the fat molecule, is polar. Therefore, in this case, the overall make the molecule of fat or oil to be polar, right? Because the molecule of fat or oil contain 2 parts. The first part is called hydrophilic, because this part is going to be the part that is actually love water, right? Because water is polar molecule. And hydrophobic is going to be the part that hates water, right? So this part right here is going to not be able to interact with water because it's non-polar. Again, water is polar. So that means in this case, you will need to see the 2 regions, and we're going to take a look at how is that going to relate it to how they are able to dissolve it within each other. Okay, so that means this fat molecule right here, because majority of it is non-polar, therefore the molecule would be non-polar molecules. Okay, so, and the ability of the 2 substances to be able to mix homogeneously in a solution, we call this miscibility. Okay, so if the 2 substances are able to mix together, we say that they are miscible in each other, or they are forming homogeneous solution. If they are not be able to mix, you will observe like 2 separate layers. For example, we say that they both are immiscible in each other, and they are going to forming a like a 2 separate layer or heterogeneous solution. Okay, so the 2 substances with the different polarity will be immiscible and forming heterogeneous, but those that are having the same polarity, they are going to be miscible in each other, which means they are going to form homogeneous solution. Okay, so the principle of this is often referred as like dissolve like, which means that the like property would dissolve in like property, right? For example, polar will be able to dissolve in polar, non-polar will be able to dissolve in non-polar. Okay, so the reason for that is because of the intermolecular forces between two of those. Okay, so this is similar to the magnet as well. Okay, so for example, if you have two polar molecule, right, the reason why they are able to dissolve in each other because the interaction of these two molecules allow them to, right, because the polar molecule contain the partial positive and also partial negative, and partial positive of one molecule would attract to the partial negative of the other molecule of the surrounding molecule. Therefore, since they are attracted to each other, they are able to dissolve in each other. Okay, so that's what it's coming from. And if you have non-polar and polar, then because non-polar, it doesn't have the separate charge, therefore they will not be able to mix because it's missing that interaction of the partial positive and partial negative. Okay, so this is what the like dissolve like is coming from. Okay, so this is the main reason why when you have oil and water, you add them together, they will not be able to mix, right? They are immiscible in each other. The reason for that is because oil, majority of the molecule is non-polar and water is a superpolar molecule, right? So that's why they are not going to mix. So now let's take a look at the following molecule. We have PCl3 and PCl5. Okay, so we're going to take a look at molecular geometry of these two, and we are going to also predict which one will be able to dissolve in water. Okay, so let's take a look at PCl3. If I give you two chemical formula, how do we determine molecular polarity? Based off what we learned before, right? If you recall, in order to determine molecular polarity, you first will need to determine what? Molecular geometry, right? So that means in this case, we don't know the geometry of these two yet. Therefore, you will need to determine geometry first. But before we can determine geometry, you need to also look at the correct Lewis structure, right? Because correct Lewis structure will tell you about the number of electron domains and also the number of lone pairs as well. So therefore, in this case, I'm just going to go ahead, draw the correct Lewis structure first. Okay, so these are the correct Lewis structure of these two. Because PCl3 contain 4 electron domains, therefore the electron domain geometry would be tetrahedral. But because we introduce one lone pair, so the molecular geometry is trigonal pyramidal. Okay, so look at PCl5. PCl5 contains 5 electron domain around phosphorus. Therefore, the molecular geometry would be, electron domain geometry would be trigonal bipyramidal. And because there is no lone pair around phosphorus, so therefore the molecular geometry would be trigonal bipyramidal as well. The shape of the molecule that is shown here is already in the correct molecular geometry, right? Because this is the trigonal pyramidal. So I can actually determine the bond polarity and also the dipole moment by using this correct molecular geometry. So if you look up the En value, you will see that chlorine would has higher ability to withdraw electron from phosphorus. So therefore, in this case, the direction of the dipole moment will go toward chlorine. And as you see, there is nothing to cancel this direction of chlorine, right? Because they are not on the opposite side. Therefore, the overall dipole moment would go toward chlorine, which is going to go down. Okay, so that means in this case, we can say that this molecule is going to be polar molecule. Okay, and on the other hand, for PCl5, if you're looking at all of this, you will see that these two chlorine will be able to cancel each other out, right? Along with these 3 direction as well. So they are pulling electron equally in all direction in this case. So the overall dipole moment equal to 0. Okay, so PCl5 would be non-polar molecules. Okay, so now which one of these molecules would be able to dissolve in water? So that's what the miscible mean, right? So miscible mean able to dissolve or able to mix to form homogeneous solution. Okay, so in this case, which one would be able to dissolve or be miscible in water? The answer have to go back into the property that we mentioned earlier, right? Like, dissolve in like, polar would dissolve in polar molecule, non-polar molecule would dissolve in non-polar molecule. Therefore, in this case, first you will need to know what is the polarity of water. We already determined that, right? Polarity of water is that water is polar. Therefore, in order to find out which molecule is going to be able to dissolve in water, you are going to find out which one that have the same polarity as water, right? So in this case, we see that PCl3 is also polar molecule. Therefore, the answer would be PCl3 that is miscible in water, which means it's going to be able to mix with water and form homogeneous solution. Okay. However, PCl5, because it has different polarity, therefore we say that PCl5 is immiscible in water, which means they will not be able to mix. So if you add PCl5 in water, you are going to end up absorbing with two separate layers, similar to water mixed with oil. Okay. All right, so again, we are going to rely on this like dissolve like in order to predict miscibility in water. Next, we are going to take a look at the miscibility of the different type of alcohol in water. Okay, so we are going to consider first the miscibility of alcohol, which is methanol in this case, with water, and second would be ethanol in water, propanol in water, butanol in water, and pentanol in water. Okay, so pretty much we already determined that water is polar molecule. Therefore, in order to determine miscibility of this, you are going to have to determine whether this molecule would be polar or non-polar, right? So methanol contains two parts. Again, the first part would be hydrophobic, which is the non-polar part because it contains carbon and hydrogen. Carbon and hydrogen are non-polar bonds, right? And the other part would be the hydrophilic, which is the polar part because the carbon, oxygen, and oxygen, hydrogen is polar. So this molecule here, if you're looking at it, right, so the overall dipole moment would go toward oxygen because nothing will actually be able to cancel that. So therefore, the methanol molecule is polar, so therefore it's going to be able to dissolve in water. So we say that methanol is miscible in water. Look at the ethanol, it's the same thing, right? Ethanol also contains two parts as well, is hydrophobic part and hydrophilic part. So the overall of these would be polar because there's nothing to cancel this part of the molecule. So therefore, ethanol would be able to dissolve in water. Okay, same thing for propanol as well. Okay, so it would be miscible. We would expect butanol and pentanol to have the same effect, right? Because you see the same thing. You see the hydrophobic part and hydrophilic part. So, however, experimentally, the butanol and pentanol is actually turned out they are not able to dissolve in water. Okay, why is that? Okay, so what I would like you to observe is that as the number of carbon and hydrogen increased, right? So as the number of these increase, you are going to see the decreasing of the polarity of the molecule. You are going to see the increasing of the non-polarity of the molecule because you are increasing the non-polar part. So that means polarity of the molecule is also a spectrum as well. It's not like a clear cut of this is going to be polar, non-polar. It's going to be a spectrum, right? So one molecule might be more polar than the other because of its contain more polar part, or the other molecule might have more non-polar part, so it's going to dictate the overall molecule to be non-polar molecule, right? So same thing here, right? So as you see that the increasing of the hydrocarbon that present in the molecule is going to make this whole molecule to be exhibit the non-polarity greater than the polarity. Therefore, these two will not be able to dissolve in water. Now, I know that you probably have question. Okay, so what is the cutoff then? How do I know when that the polar part would win or when the non-polar part would win, right? The answer is there is no general rule for that. So sometimes you can kind of tell with the alcohol functional group here, but other molecule might not be the same, right? So that's why I don't want you to know, like, there is no like general rule for that. But what I want you to know, or the takeaway message of this for the exam would be, you will need to know that if I give you a small molecule like this that contains just one carbon and hydrogen, you will need to be able to predict right away, right, that this is going to be overall polar. But if I give you a huge structure like this that contains tons and tons and tons of carbon and hydrogen, you will need to know that that non-polar part would win over the polar part, right? Because you have a lot more number of carbon and hydrogen than the number of the polar part of the molecule. Okay, So another thing that you can also know as well is that ethanol, right, is the main composition of the alcoholic beverage, right? So we know that when you drink beer or you see vodka, they are mixed homogeneously, right? Propanol is the wrapping alcohol, same thing too, right? So wrapping alcohol sometimes come with 70%. The 70% indicate that there are 70 of the propanol in 100 of the solution, which is contain water, right? So that means in this case, these two will be able to mix.
As you see, methanol and water, they both are mixed homogeneously, so they both are miscible in each other. So that we can say that methanol is miscible in water. Okay. So the next one is ethanol in water. Okay. Ethanol in water also mix homogeneously as well. So this is also we can say that ethanol is miscible in water. Okay, so there is no separate layer, they mix. So this is why when you go buy beer, right, so there is no separation of the two layers of the liquid, because ethanol, which is the main component in alcoholic beverage, is able to mix in water. Okay. The third one is propanol, which is the wrapping alcohol, right? So wrapping alcohol can also dissolve in water as well. So wrapping alcohol is, or propanol, is able to be mixed homogeneously with water. So we can say that propanol is miscible in water. Okay. The next one is butanol. Okay, so when we increase the size of the carbon chains, you will see that the polarity of the butanol will be less and less and less polar. So eventually it will come into the point where it will not be able to mix with water to form homogeneous mixture anymore. That is the reason why you see two separate layers here. So how do we know which layer is going to be butanol or which layer would be water? That's when you will need to look up their density. The one that have a higher density would be in the lower part, right? The one that have lighter density would be in the top part, right? So this one would be water, the top part would be butanol. Okay. So the next one is pentanol. Again, as you increasing the size of carbon chain, the molecule become less and less polar. Therefore, you are going to observe two separate layer also. So it doesn't form a homogeneous mixture. So that means in this case, pentanol is unable to dissolve, or it is immiscible in water.
So the conclusion of this is that as the number of nonpolar parts increases, the polarity of the molecule will decrease. Next, we are going to take a look at the miscibility of the different alcohols here in hexane. Okay, so hexane is the hydrocarbon molecules that is nonpolar because of these are composed of carbon-carbon bonds and carbon-hydrogen, which are nonpolar bonds. It make the whole molecule to be nonpolar molecules. Note that whenever that you see carbon-hydrogen or carbon-carbon, those are the part that is going to exhibit nonpolar part. Okay, so in this case, as we determined the methanol molecule earlier, right, so it's contain both hydrophobic and both hydrophilic, right? So in this case, we see that the polarity would be strong, it will have stronger effect than the nonpolar part. Therefore, you are going to observe that the methanol is going to be immiscible in hexane, which means that they are going to not be able to mix. When you have ethanol to dissolve in hexanes, you are going to see that the ethanol will be able to dissolve and make homogeneous solution with hexane. Same thing for propanol, butanol, and pentanol as well. The reason for that is because as you increase the nonpolar part, you are increasing the nonpolarity. Therefore, this molecule will be able to dissolve in the nonpolar molecule. Okay, so it's using the nonpolar part to dissolve in that.
In this case, hexane is a nonpolar molecule, water is a polar molecule, and as you see, you observe the two separate layers, like what you see before when I show for the butanol and pentanol mixed with water, right? So this is not a homogeneous solution, so therefore in this case, these two mixture do not mix, so we call this that hexane and water are immiscible in each other because polar cannot dissolve nonpolar. Okay, so again, how do you know which one is what, right? So you're going to look up the density and you will see that water would be heavier than hexane. So water would be on the bottom and hexane would be on top. Okay, so now we know that hexane would be nonpolar because it did not dissolve in water. So I'm going to check hexane with the rest of the other type of alcohol as well. For example, in this case, I mixed between hexane and methanol, right? So you will see the two separate layer also. Okay, between hexane and methanol. And again, the methanol would be more polar than hexane, so that's why there are two separate layers here. Okay, so methanol and hexane are immiscible in each other. And if you continue mixing or increasing the size of carbon, you will see that as the carbon chain increasing or the nonpolar part increasing, the molecule of ethanol becomes slightly more nonpolar, so that's why it's able to mix with hexane. So that's why you see the homogeneous solution is forming for the mixture between hexane and ethanol. Okay, and same thing, right? If you start increasing more and more carbon chain in the alcohol molecule, right, you are going to see that the molecule become more and more nonpolar. So that's why they are able to mix with hexane, right? So propanol will be able to mix with hexane homogeneously. Okay, same thing for butanol as well, right? So as you increase the number of carbon to 4, right, it's going to make the homogeneous mixture also. Okay, so that last one is pentanol in hexane. Right, so this is also more nonpolar and dissolve in nonpolar, right? So it's going to form homogeneous mixture also.
There are many applications of the molecular polarity and miscibility in real world. For example, in extraction or even in the vitamins that we eat, right? For example, vitamin C here. If you're looking at this molecule of vitamin C, you will see that it contains the polar bonds, which come from the bond between oxygen and hydrogen, carbon and oxygen, and also carbon and oxygen double bond as well. And it's also contain a small part of the nonpolar, which is the CH part. However, in this case, you will see that there are a lot of the polar part. Therefore, it's making this molecule to be polar molecule, right? There are a lot of like oxygen and hydrogen polar part. Therefore, in this case, vitamin C will be able to dissolve in water because it contains the hydrophilic part. So therefore, vitamin C is miscible in water. So that means that when your body consumes too much vitamin C, our body will be able to get rid of vitamin C just through urine, right? Because the vitamin C can dissolve in water and our body can excrete that through urine. On the other hand, if you look at the structure of vitamin A, you will see that the vitamin A contains a lot of non-polar part or hydrophobic, right? So CH and C bond. And it's contain only a tiny bit of the polar part, which is OH bond right here. So it's making this vitamin A to be non-polar molecule. Therefore, vitamin A will not be able to dissolve in water, okay, because it contains a lot of hydrophobic part. Okay, so it's not able to dissolve in water, or we call that vitamin A is immiscible in water. Therefore, when your body consumes too much of vitamin A, it will deposit in our fat body, and eventually our body can get rid of vitamin A through liver instead. Okay, so again, so this is going to be able to dissolve in fat, right? So fat soluble because fat is nonpolar. So this nonpolar molecule would dissolve in nonpolar molecules such as fat. So here is the summary of this video. We talk about the polarity of the molecule by looking at the molecular geometry, determine polarity of the bond, eventually look at the overall dipole moment to determine the polarity of the molecule. And for miscibility, we use the like dissolve like, right? Polar dissolve in polar, non-polar dissolve in non-polar. And here's the joke for you. Okay, so after you finish watching this video, again, please start working on part 2, chapter 6.2 homework.